Okay, so it's 2:30, so let's get started. So I'll also be talking about minimum spanning trees. And today will be a different type of different algorithm than Prim's algorithm. But it's also a greedy algorithm. And it shows you a different way to build minimum spanning trees, okay? So any questions about Prim's algorithm from last time? Okay, so now let's talk about Kruskal's algorithm. Right, so again, what is a minimum spanning tree, right? I give you a graph, the edges have weights, and basically a minimum spanning tree is the cheapest way to connect the graph, okay? So it has lots of different applications, but it's like a fundamental, tool that you may want on a graph. So what that means is I want a tree that's spanning, which means, right, it connects every vertex. So another way to say it is between any two vertices, there's a path. And I want to pick the subset of edges that has the smallest cost, okay? That's why it's called minimum spanning tree. So last time we saw a greedy algorithm to find a minimum spanning tree, and today we'll see a totally different, but also a greedy algorithm, okay? So let's get started. Okay, so this is an example of a minimum spanning tree, right? I give you a graph with weights. I want a tree that has the least cost, okay? Okay, everybody know what a minimum spanning tree is, Prim's algorithm, all that. Okay, if not, please feel free to ask me. Okay. All right, so let's get started. Like I said, right, for minimum spanning trees, they're not always, there's not always a globally optimal minimum spanning tree. For example, right, just take a graph where all the edge weights are 1, right? Then any tree is a minimum spanning tree. But it does turn out that if the edge weights are different, minimum spanning trees are unique, okay? So Kruskal's algorithm is a totally different way to find minimum spanning trees. And right, so how did Prim's algorithm work, right? Prim's algorithm worked by adding one more edge to the tree, right? I have a partial tree, and I say, okay, what is the next best edge to add? Well, is this the edge that connects the partial tree to the rest of the unconnected graph of least cost, right? So that was Prim's algorithm. Now Kruskal's algorithm is going to be doing something totally different. Instead, it's going to be building a tree, not one at a time, but sort of like simultaneously across the entire graph. And we'll see an example. But okay, so let me just describe to you at a brief high level what Kruskal's algorithm is doing. Okay. So right in the beginning, right, we have no tree. The tree is empty. Okay, great. And now Kruskal's algorithm is going to be doing the following. Okay, it looks at all the edges, and it sorts. It's not short. It sorts the edges from smallest weight to largest weight. Okay, and this kind of makes sense, right? Because in minimum spanning tree, we care about edges that are of smaller weight. So it sorts all the edges. Okay, and now how do we construct the actual tree? Well, in the most basic way, you loop through all the edges, and you say, okay, can I add this edge and maintain the fact that it's a tree? Okay, so what does that mean, right? I only add an edge if it doesn't create a loop. Okay, so I run through this, all the list of edges, and I say, okay, from the smallest weight to the largest weight, and I say, okay, can I add it to the tree as long as it doesn't create a loop? Okay, so what this means is it's sort of going to be creating the tree in different pieces. But every sort of piece is going to be a tree, okay? It's like not going to have any loops. But it's not, initially it's not going to be one connected thing, okay? So just to show you a quick example, okay? So this is a nice example on Wikipedia, okay? So let's just wait for it to, reset. So here are the vertices of the circles, and the edges are not drawn. The edges are just like all the plane distances, right, in the plane. Okay, so it's a fully connected graph, right? So first, it sorts all the edges by weight, and it's trying to add like smaller and smaller edges, but it keeps adding them as long as they don't make a loop with any of the existing edges in the graph. Okay, right? So you can kind of see like how it's creating the graph, or sorry, the tree, like in different pieces, but at some point it'll say, okay, can I, right? Like you can see, right? It says, right? Can I add this edge? And it says, oh well, if I added that edge, it will create a loop with already existing edges, so I'm not going to add it. I skip that edge, okay? So right in the end, right, it's like checking for lots of edges, and most of them will make loops, so then it's not going to add them, okay? So at least at this high level, like, does the description of Kruskal's algorithm make sense? Okay. Any questions, comments? Okay. So let me go back to my slides. Yeah. Okay, like I said, right, just to recap, Kruskal's algorithm, it sorts all the edges, goes from the smallest edge to the heaviest edge, or the edge with the most weight, and it says, okay, can I keep adding the edges, and as long I keep adding the edges as long as it doesn't create a loop, okay? So that's Kruskal's algorithm. So we need to check two things, right? Why does it create a minimum spanning tree, and also what is the running time of this, and can we make it faster, okay? Yeah.
How do we check if like an edge is selected if it doesn't form the loop or not?
Yeah. So we're going to see that. That's actually going to be a very non-trivial thing to check. And there is a naive way to do the checking, which is, right, I form a partial tree, and I say, okay, can this edge form a loop? What I do is I run BFS or DFS from both endpoints, or one of the endpoints. But we're actually going to see a much better way to do this check operation, right? Yeah. So I haven't told you how to implement this smartly, but at least you can imagine some way to implement this, okay? All right. Any questions before we get into the specific, the specific details on how to implement, running time, and so on? But just at a high level, does this make sense? How Kruskal's algorithm works? Okay. So let's see an example. Okay, so this is a graph, right? The black edges are the actual edges in the graph. They all have weight. And you say, okay, how do I build a tree, right? So first, I sort all the edges. So this is the first edge in the sorted order, the second edge, the third edge, and so on. And I try to build this graph, try to build this tree by adding these edges in this order, as long as it doesn't make a loop, okay? So in the beginning, right, the first edge is fine, the second edge is fine, third edge, fourth edge, fifth edge, sixth. But at some point I say, okay, can I add the seventh edge? But you can't, right? Because it will make a loop with the existing edges. So you say, okay, I'm not going to add the seventh edge. 8, same thing. If I add it, right, it's going to make a loop with the existing edges. So I don't add it. 9, same thing. And then 10, and then I'm done, right? All the edges have been finished, okay? Any comments, questions? How this thing came about? Yeah.
Oh, do you mind explaining also why the segments cancel out?
Yeah, so what are these blue things? So first, right, there's just a graph, which are just these black edges and the thing, okay? So then we sort the edges. So the blue things are like the edges in sorted order by weight. So the 1 means, right, this is the smallest edge weight, right, 3. The 10 is the largest, 15. So we go through these edges in this order, and we say, okay, I keep adding these edges to the minimum spanning tree, right? So it's a tree, so it cannot have a loop. So I only add an edge if it doesn't make a loop with the already added edges before, right? So at some point, right, I added all these orange edges, and at some point I have to consider this edge, and I say, okay, can I add this edge? If I add this edge, right, it's going to make a loop with the 2 already existing edges. So then I don't add it. So that's why these are crossed off. Okay. Yeah. Any other comments? Questions? Okay. So the interesting thing about this algorithm is right, it's not building the tree one edge at a time. It's kind of doing its own thing, right? Initially the tree could be really disconnected, right? There's different pieces, right? As you saw in the the thing earlier, right? The tree can be in different pieces, and only at the very end does it all come together. Okay. All right. So So first, I'll prove that it actually gives you a minimum spanning tree. And then later, I'll talk about like how do I implement this algorithm, right? So this step where you check if an edge forms a loop is actually pretty interesting. And there are some naive ways to do this, but actually some very, very clever ways to do this. And it's pretty cool. So we'll see that in a bit. But first, let's prove that this actually gives you a minimum spanning tree, OK? All right, so like I said, with with minimum spanning trees, there isn't really much that you need to do. Essentially, the only thing this matters is this cut property that we talked about last time. So just to remind everyone, right, what is the cut property? Essentially, it says, OK, if I just divide the graph in two, OK, arbitrarily, meaning I take a subset of vertices and the other subset of vertices, and I see the edges that are crossing the cut, the minimum spanning tree will always contain the lightest edge crossing the cut, OK, the smallest edge weight. So that's the cut property. And essentially, right, this makes sense because a spanning tree has to connect the graph. So at some point, it has to go from one side of the cut to the other side. And it better take the smallest edge, because if not, right, we could add the smallest edge, it'll form a loop, and then you take away any other edge, okay? And that will improve the tree, meaning it's not the minimum spanning tree, okay? So, right, in Prim's algorithm, we showed that, right, Prim's algorithm is always adding edges that are valid for a minimum spanning tree because it's always picking the lowest edge crossing a cut. And what was the cut? The cut was just the subset of the tree that's connected and the rest of the graph. So if you pick the lowest edge weight that extends the tree by 1, then that's valid, right? That's the cut property. And that's how we prove that Prim's algorithm is optimal, OK? So essentially, we're going to be using the same ideas. That's like the only property of minimum spanning trees that is ever relevant. But it's pretty powerful, OK? So we're going to be doing the same thing. We're going to show that, right, at any point, the tree constructed by Kruskal's algorithm is always a subset of some minimum spanning tree, OK? Just like in Prim's algorithm. Okay? So what that means is every choice that Kruskal's algorithm makes is a valid choice. Okay? That's essentially what we want to show. Like in Prim's algorithm, right? Every choice that Prim's algorithm made was a valid choice. Same with Kruskal's algorithm. Okay? All right, so right, how do we prove this? Well, we use the induction, right? That's the only tool we have in this class. All right, in the beginning, the tree is empty. There's nothing to do. And now, right, just like in Prim's algorithm, we have to be smart about what is the cut that we're looking at, right? Because we can choose the cut, right? The cut property says for any cut, the minimum spanning tree is picking the smallest edge. And in Prim's algorithm, the cut was pretty natural, right? It was the cut that's separating the tree that's connected and the rest of the graph. Now we're going to have to be a little bit smarter. But now, OK, so let E, U comma V, be the edge that Kruskal adds, OK? We want to show that it's actually the minimum edge crossing some cut, right? That's enough. Because if it's the minimum edge crossing some cut, then, by the cut property, right, it's part of some MST, and then we're happy. OK, so what is the cut that we're going to consider? Well, right, so we're going to consider the connected component that this vertex U is part of, OK? Right before we add the cut, right? Add the edge. So let's just say this was U comma V. And right, why do we add this? Right, it was like, OK, it's part of some existing component. Right, there could be many connected components in the graph. But U comma V is part of some connected component. And that's the cut we're going to look at, right? We're going to look at everything, the connected component containing U just before we added the edge. And then everything else, OK? So that's the cut we're going to be looking at, right? So why must this edge cross the cut? Well, right, we want to show that this edge that we're adding, U comma V, is crossing this cut. So that's essentially by how we pick the edge, OK? Right? If this edge was not crossing the cut, that means it's an edge in the same connected component, OK? Meaning U and V were already connected, OK? That means if you add the edge, that would have made a loop, and we didn't add those edges, OK? OK, so let me just go back to the graph, right? This diagram. So first, I need to show that this edge I add, U comma V, is going to be crossing a cut, OK? So the cut is going to be defined by the connected component that contains U right before I added the edge. So I say, OK, why did this edge cross this cut, right? Why did it go from the A side to the other side? Well, if it didn't, right, if it was just in the A side, right, let's pretend this node was here, it was already part of the connected component, then that would have made a loop, okay, right? That means there's already a way to go from u to v, and then I added another edge, so that must make a loop. And I didn't add any such edges, right? In the description of Kruskal's algorithm, I explicitly said I'm not going to add any edge that forms a loop, okay? So that's why the first part is true. Like, it is an edge crossing the cut. All right? Does that make sense? Okay. So then the next thing I have to show is it is the lightest edge crossing the cut, okay? And any idea why that's the case, right? What happens if there is another, like, better choice? So what do we do, right, in the very beginning in a Kruskal's algorithm? Yeah. Yeah, exactly, right? We took all the edges and we sorted them first, right? So in particular, right, if there was another edge crossing the cut, that would have been considered before this edge, right? Because we went in this sorted order, all right? Right, if there was another lower cost edge, then of course I would have considered that edge first, right? Because I'm going in sorted order. So that means, right? I mean, this is a bunch of words, but that just means like, well, that wouldn't have happened, right? If it must be the smallest edge that crosses that cut. Otherwise, right, that other edge E prime would have been considered first, and that would have, crossed that cut already. Okay, that's all this is saying. Okay. So going back to the diagram, right? Like I said, we need to find a clever cut to look at to show that the choice that Kruskal made is a valid choice. The cut we look at is, the connected component containing u right before we add this edge u comma v. We say, oh well, first it is a edge crossing the cut, because otherwise, right, it's an edge connecting the same component, but that would have made a loop. We didn't add those, and it must be the lightest edge, because if another edge was lighter that was crossing the cut, well, that would have been added first already, right? Okay. So, it seems like a very slick proof, but it's actually pretty interesting. So, if you didn't understand it, like, go home and try to think why these two properties are true. All right? Questions? Okay. So that's the power of the cut property, right? Like, it's the minimum spanning tree picks the smallest edge across any cut. So we can choose the cut to look at. Okay, so that's why, that's kind of why, like, algorithm design and sort of mathematical properties go hand in hand. Like, we're exploiting something to design a fast algorithm, okay? All right. Any questions about the proof? Anyway, okay, and then the rest, how do we follow, right? It's kind of like the same as Prim's proof, right? Okay, then it must be a valid choice by induction, hypothesis, blah, blah, we're done, okay? So then the rest of the proof is the same. Okay? All right. But really, like, the kind of the high level, takeaway is Kruskal's algorithm only adds valid edges, because those edges, you'll be able to find a cut where that's the cheapest edge across the cut, okay? So that's the high level takeaway. So at least that proves, right? That proves that Kruskal's algorithm is a valid algorithm, okay? If we could implement it, it will give you the optimal minimum spanning tree, okay? Or a minimum spanning tree, okay? Right, so let me just go to the, the naive description of the Kruskal's algorithm, right? So what did I say, right? I said, first I sort all the edges. That takes m log n time, okay? Right, because there is, at most n square edges, right? M is at most n square, and m log m is m log n, right? Big O. And then the non-trivial step is I need to, like, check if an edge has been, forms a loop, okay? So that's the step that's going to require some interesting implementation, okay? All right, so let's do the naive, naive thing, which is, right, I have some, small connected components throughout the graph, and then I pick a new edge, and I say, okay, is this edge going to form a loop? How do I know it's going to form a loop? Well, what I need to do is I need to check if this edge u comma v, if these vertices are already connected. Okay, so how do I check if things are already connected? Well, I run BFS or DFS, okay, from u. And so, okay, I run from u, and if v ever appears, then I know they were connected. There's a path. So if I add that edge, that would make a loop, right? So I don't do that. So that's the naive way to implement this algorithm, okay? So basically, I have m edges I'm going through, and every time I need to run BFS or DFS, that's going to take O of n time. So the total running time is O of mn. Okay, so somehow m times n already dominates m log n, right? So in the asymptotic notation, you just get O of mn. Okay. At least, does that make sense, like the naive implementation? Questions? Yeah, if this doesn't make sense, this is a good place to ask. Okay, so now what is the bottleneck? I mean, I kind of flashed it, but what was the bottleneck here, right? Like, compare this to Prim's algorithm, right? Prim's algorithm took O of m plus n log n time. It's very, very fast. Here it's very slow, right? I'm multiplying m times n. That's worse than adding them, right? Obviously. So it's very slow. So what is the bottleneck here? Yeah. Yeah, so the bottleneck is if checking if things are connected, exactly, right? Because I'm doing this n time, okay? Sorry, I'm doing this m time, right? Every time I see an edge, I need to check if the endpoints are already connected, okay? So that's, there's m edges, and I'm doing it n time, right? That's a lot of, I'm doing this operation over and over again, okay? So then the next part of this class is going to be about how do I make this checking operation fast, okay? So there's a pretty cool way to do this, and right, I'm checking for connectivity. That's the bottleneck. Okay. So essentially, right, so now we're going to take a side detour and talk about a different data structure, okay? And the data structure is only optimized for one thing, okay? It's not useful for anything else except for this one particular task. And we're really going to like optimize the heck out of it, okay? So essentially, all this data structure is going to be good for is I give you two nodes, and at some point it's going to say, are those two things connected? And then I can add some edges to the graph, okay? So it's basically it's going to I'll be answering like are nodes connected queries, okay? That's all it is doing. And it has like a few names. So it's called disjoint set or union find data structure. And it's like a very, I mean, we're not going to see like the entire history of this. We're only going to see like one version, a simpler version of this data structure. But it's only good for one thing, okay, which is to check if two nodes are connected already. Okay. So this data structure has the following three operations, okay? So right, I call it disjoint set. So what we're going to think about is we're going to think about every connected component in the graph as a set, okay, as a set of nodes. And I'm going to make the following operations, okay? First, I have to make some sets, okay? So it's going to be I'll be initializing some set. That's the first operation. The second operation is the important operation is called union. I take two sets and I merge them. I make them the same set. What that corresponds to in the graph is right. I may have some two connected components in Kruskal's algorithm, and at some point I might add the edge connecting them, right? So I need to know that they're in the same connected component, right? I need to know that they're all connected to each other. Okay, so that's the union operation. And in same operation, okay, meaning are two nodes in the same set, meaning another way to think about it is are two nodes in the same connected component, right? So previously we answered that using DFS, right? Each time we answer it takes O of n time, right? Well, actually we're going to do much better. We're going to do almost constant time, okay? So it's pretty crazy, but we're going to be able to do almost constant time, okay? But right, kind of abstracting away from the graph, what we can say is right, we have a bunch of sets. And the operations I do is, right, I make a new set with a new element, I merge some sets, and I check if two elements belong to the same set. Okay, so these are the operations that I'm going to be doing. Okay? And of course, there's different ways to like implement this data structure. Like one thing you could do is you can just like for every item just keep track of which set it belongs to, right, explicitly in a dictionary, let's say. But the thing that makes it hard is like, okay, then the union operation will be slow. Then I need to merge two dictionaries, okay? So, but what we want is we want all these operations to be fast altogether, okay? Simultaneous. So that's the hard part, right? Like if I only care about, okay, making one of them fast, then that's easy, but I want all of them to be fast simultaneously, okay? Any questions? So I haven't told you how to make this data structure, but these are just like the queries or the functionalities that I want from this data structure, okay? It's only good for these three operations, okay? All right. So then, right, if I have this like data structure, then I can implement Kruskal's algorithm as follows. Essentially, I'm rewriting it, right? So right, in the beginning, the tree is empty. So what do I do is I make a disjoint set data structure for every node, right? Because all the nodes, they're all empty. The tree is empty. And then, right, what I do, right, I iterate through the edges, and I say, okay, if an edge is connecting a connected component, right, then I don't want to add it. The same thing, right? Like if is same, in same or whatever. Are they in the same set, right? Same connected component. If no, then I add it. If yes, I don't, right? Yeah, so like I said, right, if they're not in the same connected component, then I add the edge. But then I have to merge their connected component, right? Like, so that's why we need both the in-same operations and the union operations, okay? So all I'm doing was rewriting Kruskal's algorithm, but now using this language of this disjoint set data structure, okay? So I hope that you can see that this is essentially the same algorithm, right? But now right, instead of being vague about what it means, right? I'm just saying I have this data structure that can allow me to do these operations, and I'm going to write Kruskal's algorithm in terms of these operations, okay? Comments? Okay. But yeah, but I hope you see that it's the same as Kruskal's algorithm that I said before, okay? If not, this is the right time to ask. Okay, and then and then it's like, okay, what is the running time if I have this this data structure in the sky? Well, it's basically how many times am I calling these operations, right? In the beginning, right, I have to sort, that's m log n. I have to make some sets, right? That's n times the time to make one set. I have to do this in same operation, right? M times for every edge. And then I have to do this union operation, right? At most n minus 1 time. And that's because, right, there are only n minus 1 edges in the tree, right? That's a tree. So that's the only time I'm merging things, right? Every time I add an edge. So that's only n minus 1 times of union, okay? So, whatever data, right? So if I use, DFS, right? Well, make set, okay, that doesn't cost me anything. In same, well, that costs me O of n time. And union, right? If I just keep a adjacency, list or matrix, right? That's O of 1 time. So, right, in the DFS kind of implementation, this was the bottleneck. It took m times n time, okay? But right, like I said, we're going to see faster ways to implement this data structure, okay? All right. Okay, so I guess does this expression make sense? Like I'm just keeping track of how many times I'm calling, union operation or make set operation or is in same operation, okay? All right, so now we're going to see how do I, different ways to implement this disjoint set data structure, okay? We're going to see 3 ways. There's actually a 4th way that I won't show, which is like not complicated, but the analysis is really complicated somehow. But we're going to see the 3 most basic ways, okay? So the first way to implement this disjoint set data structure, and actually this is a really cool exercise to do at home, which is the 3 ways that I show. Try to implement them. They're not very complicated, and you'll see hey, even though I just added 1 tweak, it just becomes a lot faster for some reason, okay? So that's pretty cool. So the first way to implement this disjoint set is every set will be represented as a linked list, okay? So here, let's say I have a set of 7 elements, right, 1 through 7. So what is a linked list? A linked list is basically I have a pointer from one element to the next, except I'm going to change the data structure a bit by also adding a pointer from every node to the head, okay? So linked list will just be like this 1 to 2, 2 to 3, right, the standard linked list. But now I'm going to add a pointer from every node to the head, okay? That's one change I'm going to make. And the other change is let's say I'm going to add a pointer from the head to the tail as well, okay? So it's just a list with some extra pointers to keep track of who's my head, okay? Right, and then if you're running in, you don't need to really care about pointers, right? And if you're doing this in any programming language, right? You just remember the head is like the index 0 position, right? So you don't really need it. But let's be a little bit more precise about it, okay? So we're going to represent every every set as a linked list with these pointers, okay? And now we have to check, okay? How do I do the following 2 operations? How do I check if 2 things are the okay, yeah, let's do it right now, right? How do I check if 2 elements are in the same set? Now, what is a fast way to check? Right? How do I? Yeah, exactly, right? So how do I check that 5 and 7 were in the same set? Well, right, I just go to 5, what is the head of 5? 7, what is the head of 7? If they point to the same number or the same element, then they must be in the same set, okay? All right, so or like 5 and 25, right? 25 I didn't even show. Well, 25 will presumably point to a different head. 5 points to 1, right? They're different, so they're in this different set, okay? So checking if the two things are in the same, right? So now this makes the checking part easy, right? It's all one time to check. But the harder part is going to be doing this union operation, okay? Okay, so like I said, right, make set. Well, I just make a, I just make a linked list of one element that's constant time. Are they in the same set? Well, I just check if the, whatever the head, right? I go to U, go to the head. Is it that same thing as V's head? If they're there, then they're in the same set. Now the union part, right? I have two lists. I need to merge them into one list, okay? So that's going to be the that's going to be like the expensive part, okay? So what is the most naive way to do this last operation, union operation? Well, I have two lists, right? Each of them have their own head. So I just make one of them the heads, right? So let's say I have two lists, right? A and B of lengths LA and LB, right? They're different size lists. At some point, they could be different size lists. How do I merge them? Well, let's just say I put B, right? I put B behind A, right? What that means is, right, this is a linked list, right? So I just have to, make sure the end of A points to the first of B. But the harder part is I need to update all the head pointers of B, okay? Initially, right, they're pointing to B's head, right? But now I made A the head of both A and B. So all the things in B need to point to A, okay? So that costs me O of LB time, right? Whatever the length of this B list was, okay? So that's the naive way to do it. What is a slightly smarter way to do it? So I have two lists. Yeah. Yeah, exactly, right? So that's a little bit smarter. And we'll see this in a bit, right? But the slightly smarter as well, it doesn't matter who's the head or not, right? I just make the, I only do the update on the smaller list, okay? So that saves me a little bit. And we're going to see that's going to be important, right? Asymptotically, it doesn't seem like maybe you're getting a factor of 2. But actually, over many, many operations, this is going to play a big deal, okay? All right, so what do I have? OK, so then let's just say I do this naive list implementation, okay? So then what is the runtime of a Kruskal algorithm? Well, the bad thing is like a single union operation can still take omega n time, right? Imagine the lists were like, let's say one had n over 10 elements, the other had n over 10 elements at some point, right? I need to union the connected components. At some point, right, I need to iterate through the vertices. That's going to take me n time, roughly. And right, how many unions I'm doing? I'm doing n unions. So if I naively analyze this, right, Kruskal's algorithm is taking n squared time. Okay, that's not good. Okay, n squared time is very slow, right? Prim's algorithm was O of m plus n log n, right? So it's sensitive to the number of edges, which could be less than n squared. Here it's like taking n squared time already. Okay, so that's not good. Okay, so this naive way to union is not good. Okay, it can take n time per step. But now this is the really cool part. And this is the first time we're going to see it in this class, which is, yeah, the cost of one union operation might be slow. Like at the very end, right, you might be unioning two connected components that are all huge. But we're actually going to do something smarter. We're going to show the cost of all the operations. If I add them all up, it's small. Okay, so this is a very, very clever analysis. Like one single, right, usually when we analyze algorithms, right, we say, OK, how many operations are we doing times the cost per operation. Here, we're actually going to be doing all of it all together. Okay, we're going to add up all the cost. And the total cost will be slow. Sorry, the total cost will be fast, even though a single term might be slow, okay? Somehow, essentially it's saying, right, you might be union intuitively, right? At some point, you might be unioning very, very big sets. But that can't happen too many times, right? They can only happen like at the very end, right? So essentially, that's what we're going to show. Right, the very end might take O of n time, right, at the end. But in the very, throughout the algorithm, in Kruskal's algorithm, let's say, you're not going to be unioning huge connected components, because then you'd be done. Okay, so that's the high level idea. So, but even this even works beyond Kruskal's algorithm. So just in the disjoint set data structure, right, the way I told you, we're going to show that if I do n union operations, no matter which sets I union, okay. So in the beginning, right, I have some sets, I make some sets, and I union them in any way that I want, okay. Then the total cost is going to be n log n, okay? So So what am I hiding here, right? Well, what did I not say is that, okay, in the beginning, right, you have n items, okay? They're singletons. And what I do is I union them in any way that I want, okay? I combine them in any way, whatever the way you want. And if I keep track of all the union operations that I've, the cost of all the union operations in total, after n steps, it's going to be n log n, okay? So the cool thing is, right, it's like, yeah, a single union operation might take n time even, but across a sequence of n operations, it's going to take n log n time. So that's the cool part about this analysis. We're looking at the whole thing rather than one at a time, okay? And yeah, okay. All right, so the analysis is going to be very, the algorithm hasn't changed, right? I'm still unioning these lists, except I'm just doing the minimum thing, right? I'm just doing when I union two lists, I only update the head pointers of the smaller list. But the way I analyze the running time is going to be different now, okay? It's going to be very clever. So the first step to analyze the running time is we notice the following, right? The total running time of the algorithm is proportional to the total number of times the head pointers have changed, okay, across the entire, right? Because essentially the only operation I'm doing is changing a head pointer, okay? So the keeping track of the total running time is the same as keeping track of the total number of head pointers changes that I've made, okay? That's the first observation. So essentially I just need to count for every, across all elements, how many times have I changed the head pointers, okay? Now, what I do is I look at an element, like number 5, okay, item number 5. How many times did I ever update item number 5's head pointer, okay? All right, so this is the cool part. Well, every time I update item number 5's head pointer, it was merged into a larger list, okay? Right, that's right. I'm doing this thing where I only change the head pointers of the smaller list. So if I change the head pointer of item number 5, let's say, it must be part of a list that was merged into a larger list. How many times can that happen? Right. How many times can that happen? Right. How many times can things double in size? Right. Anytime I merge something to something, right, the total thing is doubling, right? Yeah. Yeah, exactly, right? It's like every time so let me break this down, right? Every time I update, let's say, element 5's head pointer, it's in some list, then it becomes part of a list that's at least double in size, right? Because I'm putting the smaller thing behind the bigger thing. The bigger thing is bigger than the smaller thing, so it's at least doubling, right? So what this means is every time I update any element's list, or any element's head pointer, it's part of a list that's growing double in size. So I'm only updating, for every item, I'm only updating its head pointer log n times. Because at that point, right, I have n elements, I'd be done. Right? Then it's part of, this union operations would have union everything. It would just be one giant set now. Okay? All right, so this is a very cool analysis, right? It's like completely elementary. But just like by being careful of how we talk about running time, right? Instead of taking the viewpoint of lists, we're taking the viewpoint of individual elements. And we're saying every element is responsible for keeping track of how many head pointers got updated to itself. Every element will only have its head pointers updated log n times. Because every time I do that, it merges into a list that's double in size. That can only happen log n times. So then the total cost is proportional to, okay, over all the elements, how many updates do I make? Well, there's n elements. And we said for every element, I'm only going to make log n updates to it. So that's n log n. Okay? So what that proves is, right, if I do n union operations, the total running time will only be n log n. Okay? Even though a single, there could be one union operation that takes O of n time. And there will be, right, if I do it like the list way. There will be one operation that takes O of n time, but essentially there cannot be too many of these. So altogether, right, the total running time is small. Okay? So that's why I like this analysis, because it's being very careful about accounting for costs. Okay. All right. Any questions? Right. So that was a little slick. So happy to go back. Yeah. Any questions about where the n log n came from? The doubling in size, union operations, disjoint set, Kruskal algorithm. Yeah. Anything? Yeah. Yeah, exactly, right? That can only help you. It's only increasing faster, yeah. Okay, so then let's talk about the final runtime, right? Well, we sort our Kruskal's algorithm, right? We sort edges, that's m log n. Right? We make some sets. Initially, they're all the individual vertices. And at some point, right, we iterate through all the edges, and we have to check, right, are those two endpoints part of the same set? That takes constant time, right? The checking, right? Check the head pointers. But then we do union, right? How many union steps we're doing? Well, every union step causes an edge to be added in the tree. There's only n minus 1 edges, right? It's a tree, right, by definition. And we said, right, n union operations take n log n time. Okay? So somehow all these different operations end up being lower order terms, right? The thing that dominates is the time to sort. Okay, let's assume m is at least n. Okay, otherwise it's not a connected graph even, right? So somehow the disjoint set data structure running time ends up being a lower order term. The thing that dominates is time to sort. Okay, so then at least this way, right, the running time of Kruskal's algorithm is m log n. It is a little bit slower than Prim's algorithm if I use this Fibonacci heap. But Fibonacci heap is like a really complicated data structure. So actually, I would argue that like Kruskal's algorithm, right, I presented you the entire details, right, this sorting and the set operations is like probably maybe a little bit simpler. And even though asymptotically it's not faster, you know, it's a different greedy algorithm that we use. Okay. All right. Any questions about Kruskal's algorithm, disjoint set operations, n log n, doubling? Okay. Yeah, and I would say like this is a pretty fun algorithm to implement. So if you have time, right, yeah, you should implement this Kruskal's algorithm. It's pretty fun. Okay. All right, so now the rest of the class is like nothing related to MSTs, and you know it's not even related to the rest of the class. Like it won't be in the lecture or exams or homework or whatever. But I want to spend a little bit more time talking about this disjoint set data structure. So for the purposes of Kruskal's algorithm, like this is already the best you can do because even sorting the edges is already m log n. So you cannot like by improving the whatever disjoint set data structures, you can't help you. But as a problem on its own, disjoint set data structure is like a pretty interesting problem, right? I just want to maintain some sets under unions. But it turns out there's much better ways to do this data structure, right? So right, it's not too fast, right? I'm saying n union operations total take n log n time, but one operation could be really slow. So that's one thing undesirable about this data structure that I showed. The other thing is like, okay, can we make log n even smaller? Can we make it constant time? So that would be crazy. So we're going to see something like that, okay? And like I said, my name is not Manolis. It's not 2024, so I stole these notes from Manolis, but they're very good notes, okay? So yeah, so like I said, it's called disjoint set or union fine data structure. So let's just recap, okay? So now forget about minimum spanning tree, okay? Now I just care about the separate problem, which is this union set data structure, okay? So what is that problem? Just to recap, I have a bunch of objects, right? A bunch of items, and I want to keep track of how they're grouped, right? That's the union set operation, right? Like I said, I want to merge some groups, and I want to check if two items are in the same group, okay, or same set. Like I said, okay, it's basically supports 3 operations, right? The main thing being find or is same, like I said before. Are they in the same thing or union, merge 2 sets, okay? Just recap, right? So Manolis has really nice slides with diagrams, right? So in the beginning, right, you make everything its own set, and then at some point you might want to union things. And we want these operations to be fast, okay? Okay. Like I said, okay, and then, right, what is the head of 2? Well, it's the set A, okay? All right. Yeah, so why is it important for us, right? It was for these connected component applications, blah, blah, blah. So let's go to the more interesting, right? So now I'm going to show you a different way to this union set, right? It's not going to show up in your exam or homework. This is a very cool way. But it's going to be totally different than the linked list, okay? So whatever I told you about linked list, just don't remember it, okay? It's going to be a completely different way to implement this union set data structure. Essentially, the first step is we're going to form paths, okay? So it's kind of like a linked list. We're going to put all the elements in one set into a long path, okay? All right, so all the elements in A were in a long path. All the elements in B were in a path. C were in a path. And to check if things are in the same set, what we do now is we just walk up and we say, okay, this is the name of the set, right? Name is C. And I say, okay, are these two elements in the same set? They both walk up and they say, oh, okay, do I reach the same number, same name of the set, okay? So naively, right, this is very bad, right? Like I said, in this example, right, the chains can be very long, right? There's n elements in total. Some chain can be really long. So if I just walk up this chain and check, right, if I want to check elements 5 and 7, are they in the same set? Whatever chain they're on, I have to walk up. And the chain can be very long, okay? So that takes, that could take omega n time. So now I'm going to show you a totally different way to implement this disjoint set. And nothing with linked lists, wherever, we're going to use trees, okay? We're going to use trees. Right, and the motivation of that comes from like, okay, well, these were paths. Paths are some type of trees. I'm going to use a smarter tree to organize the elements, okay? So essentially, right, in the beginning, everything is its own tree, okay? Everything is its own tree, all right? And now instead of having things be paths, right, before, right, if I have a set that had, elements 1, 2, 3, and 4, it was just a long path. Somehow I want the tree to be balanced, okay? And why does that help you? Well, how am I going to check for parent, right? Sorry, how am I going to check if they're the same set? Well, I'm going to walk up the thing and I say, okay, what is the head node, right? The root node, let's say, the representative of my set. So the cost to check if things are the same is going to be the height of this tree, okay? All right, so does it make sense, right? I'm going to create some trees. Each tree will be, represents a set. And I'm going to make one of the nodes the root node. And to check if things, or like to find the set that I'm in, what I do is I walk up the tree and go to the root. And I just check if the roots are the same, okay, to see if things are in the same set. So then the cost here is just the height of the tree, okay? Right? Previously it was paths, like the long path, right? The height of the path. Now it's going to be the height of the tree. And that kind of, it's kind of leading to something, right? It's like basically saying, if I can represent every set as sort of like a balanced binary tree, then the height is always going to be log n, right? That's they're all going to be very like flat trees. So walking up to the root is going to be very fast, okay? That's essentially what we're going toward. And now, how do I merge or union, right? I have two trees. I just make one of them the child of the other root node, okay? So I just add a new, I just add like a new edge. I say, okay, I want to merge them. Well, then, this can be the new root of everything. So then I add an edge, right, that connects to the old root. So it's like a thing that's dangling off the new tree, okay? All right. Okay. Yeah, so this operation is fast. I'm just like redirecting parent pointers of just the roots. All right. So essentially the idea is like, how do I avoid creating trees that are super tall? Okay, I don't want that because then this find operation or this is same operation is going to be very slow because I have to walk all the way to the root. Okay, so I want to somehow maintain a balanced tree, but the hard part is I'm like merging trees into each other, right? So I want to make them balanced while doing that. Okay. Yeah, and right, this example just shows that if you're not careful, right? This is kind of the same thing as the linked list thing, where if I merge, if I say, okay, I have two trees, I want to merge them, right? I want to union them. What I do is I make the smaller tree the new root, and then merge the taller tree as a leaf or like as a new branch. That's going to make things grow, and that's bad. Okay, so like I said, right, and you can imagine, right, if I do this in a uncareful way, it's going to lead to a long path. Okay. So it's the same idea as the linked list, which is every time I want to merge two trees, okay? So initially they're all like singleton nodes. Every time I want to merge two trees, I merge the shorter one into the taller one. So what that means is, right, I have two trees, right? I just need to update, like, okay, I have two roots now, right? Two root nodes. Which one points to which one, right? Which one is the new root node? Well, I just say, okay, the taller tree is going to be the parent of the root of the smaller tree, okay? That's it. I could do the opposite, right? That would be bad. But it's kind of like the same linked list thing, which is I'm going to merge the shorter tree into the taller tree, okay? So does that make sense? Like, right, this tree is, okay, so I guess things are pointing up, right? Essentially, I have two trees, and at some point, I can say either this points here or this points here, right? Which one is going to be the new root? And I just make sure that the root of the taller tree will be the root of both the trees now when I merge them, okay? And we're going to see, like, okay, this is the same type of analysis as in the linked list case, where this is going to keep things balanced, okay? Essentially, the idea is, like, why would the height of a tree grow? A height of a tree will only grow if the number of vertices in the tree is also growing, because the height will only grow, right, if I'm merging two things that are balanced. Right? If I'm merging a very tall tree into a very short tree, the height is not growing, right? Because, like, the height is still based on the tall tree, right? Because I'm just putting a new pointer from the root of the tall tree to the short tree, right? Yeah. So another way to say that is, if I end up with a tree that's very tall, then it must have many nodes, okay? There can only be n nodes, so all the trees will end up only having height log n. Okay, so essentially they'll be like balanced trees. And it's kind of the same proof, okay? Yeah, so like, okay, so why did the height update by 1, okay? Essentially that's the main idea. You don't have to look at the slides. Why did the height update by 1? It only updated by 1 because I'm merging two trees that have the same, almost, that are about the same, okay? So that means things are doubling, okay? That's the main idea, right? Like, if I go back to this diagram, right? I have this big tree and this short tree. What I should do is I should have a pointer from the short to the tall, right? Because the tall node root will be the new root. That's not going to change the height, right? The height is still going to be dominated by the tall tree. That's only going to change the height if these were balanced, right? If they were about the same height themselves. But by induction, right, that means they had two of the d nodes. Okay, so that's essentially what this proof is showing. It's essentially showing, right, I only grow the tree height by 1 if I'm doubling the size of the tree, if I'm doubling the number of vertices, okay? That's the main idea. And you can read it later. It's the same kind of analysis as before. But it leads to an interesting consequence, which is like now, right, previously if I do this linked list thing, it was the cost of n unions is n log n. But now the cost of any union is only log n, okay? So now it went from like the total cost being small to every operation is small, okay? Essentially it's because this thing where you only merge the shorter tree into the taller tree will make sure that over any, at any point, okay, the height of any tree will never be more than log n. Okay, that's what it'll ensure. Okay, and that's because, right, we're gonna, right, we just showed, or I kind of gave you a high level thing. If a height is tall, it has many nodes inside. Okay. So that's the cool thing, right? Somehow we went from n log n time on, in total, or log n time on average, to log n time worst case. Okay, so a unit operation with this tree data structure will only be log n in the worst case. Okay. So that's at least some improvement, right? Like that means I don't have to do many operations to be fast. Every operation will be fast. If instead of using this linked list, I use this tree. Okay. Right. So, but somehow the procedures were roughly the same, right? I had pointers, and I'm just pointing the root to the new root. But instead, I'm just doing it by size, or like by height. I'm only merging smaller trees into taller trees. Okay, that's the main idea. Okay. Now this is where like the crazy part starts. Right. So essentially, I say, okay, the disjoint set data structure is going to be a bunch of trees. Okay, and I'm going to make sure, right, I'm doing it in a smart way so that the height of the trees are not too tall. But now I'm going to optimize it even further, okay? Even log n is too slow. I want to make every operation constant time, okay? Every operation constant time almost, which is like a crazy thing to say, right? Okay. So now what I'm going to do, right? That's why I kind of skipped over the thing, because we're going to change it now, okay? Right. Now I have trees, right? I have a bunch of trees. Every tree represents a set. Now, now I'm going to do something called path compression, okay? Which is I want to make the trees even flatter. So how do I do that, okay? So this is the trick, okay? Every time I do a find operation, so right, previously I had this in-same operation, but now let's replace it with this find operation, which basically says which set is this element part of. They're roughly the same thing. Every time I call this operation, what am I going to do, right? I need to walk up the tree, right? So I go to 7 and I say, which set am I in? I don't know. I need to go to my head, right? I need to go to the root, so I walk up. Every time I walk up, all the nodes that I encounter along the way, right, by following these parent pointers, I will take them and I will merge them. I will put them as leaves of the root, okay? So what I'm trying to do is every time I spend a long time finding something, the next time I have to find it will be very fast. That's essentially what I'm trying to do. Or another way to say is like every time I spend a long time, I'm actually making the data structure, the tree, very flat. So it's like if I spend a long time on one operation, it's going to make all future operations for those things very, very fast. Okay. Okay, so that's one trick in algorithms is like even if you're spending a lot of time, you use it to help you for the future. Okay, so in the future, right, if I ever had to do this find operation for 6, that'd be very fast, or for 7, or for 3, or for 4, right? Everything that was on the path. Okay. The merge step or the union step is still the same, right? I have 2 trees. I just make one of the smaller trees root point to the larger tree's root. That's fine. So that's still constant time. But the question is, right, if I do this path compression, right, every time I do this find operation, I make the tree flatter. What is the running time of union operations, okay? So, okay, we're not going to do this in discussion. This is just for his class. But it turns out you can prove the following, okay? If I do this one trick where at every time I do a find or is same operation, I just flatten the tree, then across a sequence of n unions, the total running time will be n times log star n. So what is log star n, okay? I'll tell you in a bit. But it's also like it's not a per operation guarantee. So per operation we had log n. This is still a guarantee where I sum across all operations. But now the sum is not n log n, right? I'm doing n union operations. The sum is n times log star n. So another way to say it is, on average, the running time is log star n to a union operation. So what is log star n? So if I give you a number n, right, log star n is the number of times I have to apply log to get to 1 or get to 2, let's say. So log star of 2 to the 2 to the 2 to the 2 is only 4. Okay, so log star n is a very, very slow growing function. Okay, so another way to say is, well, I know, I'm just going to say it again, is like, right, so what is log of n, right? It's like x such that 2 to the x is n, right? Let's pretend everything is power of 2. What is log star n? Log star is how many times do I keep applying log until I get to 2. Okay, so it's a very, very slow growing function. So if I put log star n of number of atoms in the universe, it's like at most 10. Okay, so it's a very, very slow growing function. It's much slower than log, right? It's like log of log of log of log of iterated logs. As many logs as you want until I get to smaller than 2. That's log star n. So I just wanted to show, like, right, with these tricks, right, you can get these crazy running times. Like, this is, how did this come up? It's, who knows, right? I mean, it comes up in the analysis, but the fact that it leads to this is very cool. And you can also implement this algorithm without knowing about the analysis. All I'm doing is every time I do this find operation, I flatten things, okay? Yeah. So what that means is like future find operations are faster, okay? because I'm sort of like doing a bunch of, every time I spend a long time doing a find operation. Oh, I'm sorry, maybe I said the union operation. Sorry, union operation is only constant time, right? Because I'm just changing pointers. The find operations are the slow one. It's essentially, the idea is every time I spend a long time doing a find operation, I'm making it faster for the future. So it turns out if I do n find operations, the total running time will be n times log star n. Okay, that's a cool thing, and it's not even the end of the story. Okay, there's one more optimization you can do, where the cost of every operation will be something called inverse Ackermann function. Okay, the inverse Ackermann function is the slowest growing function you'll ever encounter in your life. If you plug in the number of atoms in the universe, it'll be at most 3. I'm not gonna define it. I linked a set of notes in the canvas so you can read about it. It's pretty cool. But yeah, somehow for this data structure, you can really push it so that every operation becomes almost constant time, which is kind of a crazy thing. But yeah, this is the end, right? Yeah, so disjoint set, minimum spanning tree. Any questions? This is the end of minimum spanning tree. Yep. All right then, yeah, that's the end of the class. See you next time.